Good afternoon. Welcome to this distinguished lecture series, part of our Diamond Jubilee celebrations of IIT Bombay. We are privileged to have here among us Professor Biman Bagchi of SSCU, Indian Institute of Science, Bangalore. Throughout his ongoing illustrious career, Professor Bagchi has asked a lot of significant questions and answered them mostly using theoretical methods, statistical mechanics. At a rather young age, he became very well known for his work on solvation dynamics. Other than solvation dynamics, he has done significant work in the field of biomolecular interaction, protein folding, single molecule spectroscopy, a lot of other things. In fact, in some of our courses in this department, we discuss some of Professor Bagchi's work. So, it is a pleasure indeed to have here as a part of our Diamond Jubilee celebration. Professor Bagchi studied his BSc from Presidency College, Kolkata, followed by MSc from IIT Kanpur and PhD from Calcutta University, and he did his PhD from Brown University. He has collaborated with a lot of important people in physical chemistry, and here he is today. Today's lecture is for a general audience, I believe, and it is titled From Darwin's Theory of Evolution to Protein Folding and Back. This is the first of a series of lectures Professor Bagchi is going to deliver in this trip. Second one is on Thursday. So, without further ado, may I request Professor Bagchi to begin.
Thank you very much, Anindo, and the department for inviting me to give this talk. These days I have a rather busy schedule, so running kind of here and there, and after taking over as the Dean of Science at ISC, for a long time I did not do too much of administration. After I was a chairman for 4 years in SSU, that was way back in 2003 or 4. But administration has its rewards, but also takes huge amount of time, and so even during my stay here, that will be punctured by one trip to Bangalore and another trip to Delhi. But I will be giving 3 lectures. Second of them will be on 22nd. That will be on more theory oriented, like quantum diffusion and quantum coherence. And the third lecture I have not yet decided, but it could either be on electrochemistry, ions in motion, or it would be on chemical dynamics, which will be landscape and protein dissociation. One of the two, if lectures get ready, I might give both of them, given that if the time permits, and I do not expect such a big audience, but there will be more specific. Today's lecture came from a paper which was published recently by Ken Deal in PNAS, who used one of our earlier work on protein folding, actually pretty early work on protein folding, in a very interesting way to start address the theory of evolution. Interestingly, our theory of protein folding itself came from Darwin's theory of evolution. In order as an educational, I'll spend quite a bit of time on Darwin's theory of evolution. The reason being that I remember, I have this blog, and the few of you who read the blog, that I tell a lot of stories, and in this lecture also I will be trying to tell a lot of stories, little stories, some personal stories, some involving other things. Now, the way in my mind it all began, when you are growing up, I am a son of a school teacher and a freedom fighter, and he was quite a distinguished man himself. And as we said, as a school teacher we are not rich, far from it, but my father used to give me a lot of books, and often they are picked up in a second-hand bookstore in a college street in Calcutta. But one day he told my mother that tell Biman, we two brothers, to stay that morning. There is a holiday at 9 o'clock. He seldom requested us to stay at 9 o'clock because we are always in fields playing. He would always wanted us to go out and play. So that day, that morning, he took out 2 new books, completely new, expensive books. One of them was The Origin of Species, another was, if I remember, Survival of the Fittest by Charles Darwin. That's the first time I heard the name of Darwin. Then he spent next 2 hours explaining to us, I was in 9th grade, the theory of Darwin, and so impressed I was. My elder brother could care less and forgot the name of Charles Darwin in no time, but I went on reading many things on Charles Darwin, getting books and discussing with him. That was a stage which I never thought I'll go back again. But you will see that education and 9th grade played a very important role in developing a theory which is now perhaps the most successful theory of protein folding at the initial stage of protein folding. I have written 3 books, one of them Molecular Reduction in Liquids, that was published in 2012, that has essentially time dependent processes like activated barrier crossing, solvation dynamics, how do molecules rotate and translate in liquids, and how do we probe them in spectroscopy like Raman scattering or infrared. This book deals with that. It is based on the phenomena, not on theory, though theory comes in there. Followed up by a book which is a bigger book. They all 3 are pretty big books. These water and biological processes, and I was not happy with Oxford because they didn't allow me color figures. So I went to Cambridge, and this is a much bigger book, about 400 pages. This was written partly because of I found that we did some nice work which was not really getting, well, they cited enough, but as you always know, you want more credit for your own work. So they wrote, that took a lot of you. Last one, which was published few months ago, 2-3 months ago, this even bigger book, about 600 pages. This was written because I found statistical mechanics is not taught. I went to, the decision essentially came quite some time ago. I went to Central College. We call the Bangalore University Physics and Chemistry Department Central College. And then I looked in the syllabus. They have a syllabus in statistical mechanics, but there's nobody to teach it, you know. And one of the reasons I found that Indian students, correct me if I'm wrong, they like to read from books written by Indian authors. You know, this is very common if you go to St. Joseph's College or in college. Most of the books they study are written by Indian authors. Maybe something with the language, maybe something with the way we think. But this was a very major thing, which is a textbook. You can get it. Other 2 you get free now in a very good quality in internet. This one still is not available free internet, but people are, you probably have it in your library, this book. Okay, this is about the books, and now about the today's talk. So this is he is a very famous biophysical chemist, and this is the article I was talking, came out this year, and this is about evolution of protein. You know, we always talk a protein sequence is conserved over the years, and the robust sequence is the one that gets conserved over the evolution. Kendall addressed that question of the robustness and adaptability and stability of a protein sequence, and in that, in the theory of evolution, he used the language which is completely that of people use, the evolutionary people use that, and in that he used what was our old theory, and the idea of the talk came from that. This theory, when we developed, it came from evolution, and so it was kind of coming together. When you talk of evolution, it always this, I'm not too showing cartoons, but this is a very interesting thing, that what you are told by and large in very different forms by the society is that they don't think out of the box. But I think one of the biggest thinking of the out of the box is the Charles Darwin's theory of evolution. In 18 years ago, we all took stock of what happened in last 1,000 years, millennium. What is the most significant discovery that was done? People always think that it would be the Einstein's theory of relativity and those kind of things. No, almost by every measure, Darwin's theory of evolution was considered the most significant idea that any human being has generated. And this was the book I was talking, The Origin of Species. We will come to it more and more. So plan of the talk, I start with protein folding problem. I'll then talk a very important concept in protein folding is called Leventhal paradox. And then we'll see how we solve this paradox of protein folding in using Charles Darwin's theory of evolution, which is laid by another very famous theoretical biologist called Richard Dawkins. His book, The Blind Watchmaker. Then Hamlet, Shakespeare, methinks it is like a whistle. Then we have this theory in the construction of folding funnel. We'll go back to stability and adaptability, which is the title of the talk, the evolution to protein folding and back. We'll have something to talk about hydrophobic force law and protein folding, and then evolution at a molecular level. I'll discuss a little bit. So we'll start with the protein folding problem. And what is this problem, which is at one time from 1950s or 1960s, it was a central piece of biology, then physics, and also physical chemistry. So the protein folding problem is essentially that how a seemingly random sequence finds a unique native state. Now let me tell you what is a unique native state, and let me explain this. If I tell you now, say I suddenly burst a cracker here and say boom boom, all of you will run out, okay, with the door as fast as you can. Then when you realize that there is no bomb, you will come back. Now when you come back, if you come back in a little hurry, then you will again sit whatever places that are available to you, but you now find that your nearest neighbor least, that means the people who are surrounding you are no longer different. So if I take a sodium or sodium chloride and number all the atoms and then melt it and refreeze, every time the nearest neighbor least, that means the sodium atom 28 surrounded by other in FCC that is 12 chlorine and sodium will be different. In protein folding, that's not the case. Every time you melt the protein, go into denatured state and fold it back, every time the nearest neighbor least is the same. You find every time the same alanine is by the same valid or glycine along the sequence. So you have an amino acid which is a protein 200 amino acid long. When you fold it, it's exactly same thing. In the language of physical chemistry, that means there is a tremendous entropic cost. We fold and it folds fairly fast. Recently, 2-3 weeks ago, I came to Bombay again, and there is a talk, internet talk show called SynTalk. I don't know whether but you can read it in SynTalk. These young people who are very successful in their profession, investment banker and worker in Facebook and other places, they arrange this to bring different people from India or abroad. This time it was me, and there was a director of Econormal Superior in Paris, a very famous distinguished physicist and a distinguished writer. Three of us, we were in the talk show. That means we were taken in a studio, there was an anchor and asked us question. The subject of the SynTalk was fast and slow, and there they asked me that how come glass is so slow but protein folds so fast. They knew of my work of Leventhal paradox. That's why they invited me to the talk show. That means protein is such a complex thing and such precise long range contact formation and pair contact. How does it do it? At immense entropic cost, such a fast, some proteins are in milliseconds, some in seconds, maybe big ones in hours, but it is really fast. if you consider the complexity of the process. But in biology, in your body, proteins are being synthesized all the time, even now, and they are then put in the native state, because without native state they are not biologically active. So this Nobel Prize winning famous experiment by Anfinsen, he did both ribonuclease and lysozyme. He did the following experiment. He said, okay, let me take ribonuclease, I put 8 molar urea and then beta markaptanol, I make it denatured. I free it from urea, it goes back to ribonuclease. In denatured state, it has no biological activity. Okay, useless in our body. But native ribonuclease is the one that are biologically active. Let us look little bit this ribbon diagram of the ribonuclease. The ones that are shown here are the disulfide bonds. So there is a 1, 2, 3, 4 disulfide bonds. Okay. With beta markaptanol and 8 molar urea, these bonds are broken. Okay. So cysteine SS bond. There are 8 of them. Now look at the bonds. These 58 bonds with 110, quite long distance in along the contour. Then these are close. Why not 58 goes to 65? Then 95 bonds with 40, 84 with 26. So these are quite far. So if you ribbon diagram, they are going to quite far. So if you are aware, so there is a very intricate, quite long distance. These are called tertiary contact or long distance contact. Why does it form so far, and why does it form like that? You denatured, you get the SH back, then you refold it, again exactly the same contacts are formed. This is what I was saying, the pairwise contact is the same. Contacts are the same every time, otherwise it is not biologically active. Anfinsen repeated these experiments from 67, 68 to 70 something, and then he got a Nobel Prize. But then this was always a paradox or puzzle. How does protein do it? You know, it has so many other possibilities, as I told you. Anfinsen said native state is the most stable state, and that is called Anfinsen hypothesis. That, however, gave rise to the paradox that I am going to describe. It is a very famous paradox. This is the number one first thing that you start when you start protein folding. If you take Leninger's biochemistry or Lupert-Star biochemistry, protein folding means it starts with Levinthal paradox. Cyril Levinthal in 1968 set out to ask the feasibility of this hypothesis. And he asked the following question: how long does it take for a protein to fold into its native state? And the basic hypothesis, he was a mathematician or mathematical physicist. He said this following question: okay, see, you say somebody gets a very big salary. How do you know somebody gets a big salary? You need to know many people who get much less salary. Okay, that means we have to compare with a significant amount to know that what is our standing. It is all relative. So in order to know native state is most stable state, the protein must explore certain amount of states to know that it is most stable. Okay. So Cyril Levinthal started to find out how does it take to do that comparative study. How long a protein gets to know it is the most stable state, so that Anfinsen hypothesis is right. So he said, okay, a protein has 101 amino acids, each amino acid can have 3 states, then there are these many configurations, 3 into 10 to the 47, even if the protein samples an astronomical speed of 10 femtosecond inverse or these per year, it will take 10 to the power 27 years to try them all. So if the protein even 1% or 0.01% or 0.001% states its sample, it is just not possible, right? So something else is going on. This is the Levinthal came to know, which remain unsolved, called Levinthal paradox. This was compounded by computer simulations, but whenever we try to do in computer simulation, we are not getting protein at all we are not getting the folded state. We simulated at one time 1000 initial configurations. We are not getting anywhere close to native state. Many people tried. Now the problem is solved, but I am talking of problems which are in 1990s. So this thing I stated in the beginning, protein folds in a time scale of seconds or even milliseconds. How does it do it? That is the paradox. So again, let me state it again. Leventhal paradox, given the tremendous numerical odds against finding a unique native state, how does it occur in much short time scale? In other words, why protein folding is so slow, fast, while glacial relaxation is so slow? So now I will go back to Charles Darwin and tell you one more story. So the crux of Darwin's theory of evolution focuses on the elimination of inferior species gradually over time through a process called natural selection. So let's spend a little bit more time on Darwin's theory of evolution. This is from Wikipedia. Different characteristics tend to exist within any given population as a result of mutation, genetic recombination and other genetic variation. Evolution selects one species, we know that. That's a natural selection. And this has, so the way you and me, we are sitting and standing here is a product of this evolution. But people didn't believe it. Many enormous amount of struggle, especially from religious people, church, that he faced. So Darwin's theory of scientific theory states the evolution resulted from a natural, we all came from very origin, we have all have the similar or same origin. It's we are different, we have reached here because of evolution. We are different, that is because of evolution. Something is very significant here, artificial selection is same as natural selection. This is a very important thing, if I get time I will come back to that. So again, now second part of my story starts with this brilliant theoretical biologist called Richard Dawkins, who wrote a book, The Blind Watchmaker. Now, he is just a brilliant person. Now let me go, before I will tell one more story, let me go a little bit more. In his choice of the title for the book, Dawkins refers to watchmaker analogy made famous by William Paley in his 1801 book, The Natural Theology. This person used to give lectures. He was a very famous theologist around this time. He used to say that, say you are walking in a forest and you find a watch, a sophisticated watch, and you look at it and you wonder at the symmetry of the watch. And there is a maker who made it. Look at the celestial body, the symmetry, the complexity. Look at a flower, the beauty and perfection. And this somebody has made it. And so there is a, just like watchmaker has a maker, watch has a maker, this world, complex world has a maker. That's the God, the creator. Now A came to Richard Dawkins, took that analogy and said, yes, there is a maker, but then maker is no God. This is the blind force of nature. That's why it's called blind watchmaker. Now, let me tell you one little bit more story. So, I went to NIH and I knew nothing about proteins. I knew protein are carbon, consists of carbon and nitrogen, nothing more than that. I already got my Vadnagar in already, that means I was reasonably well in physical chemistry, pretty young those days. But I knew nothing of protein. I said I am going to have nothing to do with proteins. This is too complicated. But after going to NIH, I went to work with a person who is my mentor, Bob Zwanzig. I have written 2 blogs about Bob Zwanzig. Amazing person, amazing scientist. He would have got the Nobel Prize in 1978. He was in the final 2, but politics was made and it was given to Prigozhin, who was much inferior scientist to Bob Zwanzig. Now, Professor Zwanzig, I went to work with Professor Zwanzig. I once worked with him before as my postdoc. So again, I went to him in NIH. However, after landing there, first 3 or 4 talks were nothing but protein folding and nothing but Leventhal paradox. And all physical chemistry seems to be working on, the physicists are working on protein folding, and it was NIH, National Institutes of Health in Bethesda. So I went to our lab chief, Bill Eaton. Zwanzig was no help. When I tried to read proteins, he came to me one day and told me very disapprovingly, "Oh, you are reading these things, so you will be talking of histidine, proximal histidine, distant histidine." So very discouraging. So then I went to lab chief Bill Eaton and asked, Bill, what do I do now? Bill looked at me even more disdainfully and told me, Biman, for a physicist like you, you should go and read Blind Watchmaker by Francis Crick, What Mad Pursuit by Francis Crick. See, I was in really bad shape. So I even took all the disdain of Bill Eaton and Bob Zwanzig and started like a good student, Francis Crick, the What Mad Pursuit. Bill Eaton later told me that he really made fun of me because what mad pursuit means your whole pursuit is mad, whatever. So I started, and I used to take a bus from Rockville to Bethesda, bus I still remember T4, and I started reading that and then I came to chapter 3 of Francis Crick, and that's title of the chapter was Blind Watchmaker. And there he discusses everything of theory of evolution. Then I remember, gee, I know this stuff. And there Richard Dawkins does this wonderful thing. He was discussing Paley's watchmaker, the theologist Paley. So he gave this example. He said, okay, let us consider a monkey typing Shakespeare's sonnet. This is Richard Dawkins, the Leventhal paradox or protein folding by Shakespeare and Darwin. So Richard Dawkins gets that, let's see a monkey trying one line of Hamlet, and that line is, methinks it is like a weasel. Here the Hamlet, Prince Hamlet and Polonius, his friend, are having a conversation. Hamlet, do you see yonder cloud that's almost like a shape of a camel? Polonius, see, the friend is conscious of the fact that his friend is the prince, so whatever prince is saying he is repeating. By mass, it is like a camel. Indeed, Hamlet said, methinks it is like a weasel. Polonius, it is backed like a weasel. Then Hamlet goes, or like a whale. Polonius said, yes, very much like a whale. Very interesting. Now, what Dawkins did the following, methinks it is like a weasel. Then how long now, if it is a random process, Leventhal paradox assumed it takes so long, but it's a random process. So a monkey trying to type Hamlet, these methinks it is like a weasel. How long will it take? That's what Dawkins asked. Now there are 28 characters there, methinks it is like a weasel, 6 blanks. 27 possible choices for each of them. 26 letters plus blank. Random attempt by a monkey, this many keystrokes. But then Dawkins said, if the monkey cannot change the letters correctly in space once, then it's a few thousand strokes. And I did that experiment, 2200. When I read this first time, I was so excited. I came down immediately, wrote a small Fortran program. Those days we used to write Fortran program. And then I looked for Cyril Levinthal's paper. I couldn't get it, because it's 1968. But then I requested NIH, then they gave me a microfiche and I could develop the paper, and it was 1.5 page long paper. And then that evening I went to one of my friend Richard, Attila Szabo, and told him that this is, I knew that this is a secret of protein folding at least at some level, how it is so fast. Then we started building a theory, and now we are to a physical chemist now. I want to have a general theory to give the qualitative discussion I gave it to above. It didn't have a general theory, Richard Dawkins. It is interesting, after we made the paper, now Blind Watchmaker, Richard Dawkins, theory of evolution, all discussed with the monkey. But before that, it was not there. So now I want to do a very simple, tiny little calculation. Let me simplify everything. Consider 2 states per bond connecting amino acid sequence. So you have the beads, okay, and bead can have 2 states separated by a barrier. Correct goes to incorrect. When it is correct, I give it a number 1, incorrect I give it 0. Correct to incorrect goes to a rate k0, incorrect to correct goes to a rate k1. Now, if it is a process correct to incorrect, incorrect to correct with a forward and backward rate, k0 by k1, ratio of the 2 rate constant, what is that? Equilibrium constant, correct. And what is this most important relation of physical chemistry? which connects chemical kinetics and thermodynamics? Louder. Delta G RTLNK, delta G equal to minus RTLNK, right? Equilibrium constant. So ratio of the two rates gave me equilibrium constant capital K, and that is reconnected to thermodynamics, correct and incorrect. So bias, free energy difference is the bias. Then we did something which is called mean first first time, but till now things are very simple. Each correct gets number 1, each incorrect gets 0. I sum it up at any instant configuration. Number of correct is S, set say. So I define all the numbers I add, then that is equal to S. I have a delta function which just picks up. When this thing becomes equal to that, that picks up. And this I do many times. This angular bracket means I do many times. Okay, that gives you a probability. So once I have the probability, I now say rate S goes to S plus 1 because n minus S are wrong ones. That incorrect to correct, total correct S to S1 this. When I do all these things, and there are something, this is nothing but what is called chemical kinetics, simple chemical kinetics I am doing. But in a collective variable now, that is what I meant, that we need to do collective variable, we have to put certain basic kinematics there, okay. This one has a very powerful method in time dependent statistical mechanics, which in my book you have, which is called the technique of mean first first time, which is called adjoint, and we can solve that equation. Once you solve that equation, you get an expression of like that, k0 by k1, this is equilibrium constant, right, k0 by k1, just you said equilibrium constant. Now there is a degeneracy part bond nu, which in our case 2, and u is the difference. I should have been delta G0, doesn't matter. Now I say, okay, time tau S, very careful, is the time starting from S, number of correct bonds to go to all correct. That what gives it that. That has this form. Now this is the equilibrium constant, so I can K, this quantity is like this. If I now increase that from, this is in unit of kBt, kB is Boltzmann constant, T is the temperature. So this kBt which comes everywhere, which is nothing but RT, kBt multiplied by Avogadro number is RT. How quickly you see, all I had to have a favored correct one just by about 1 kBt, and it goes from 10 to the power 30 years to 1 second. This is called law of large numbers, many things are happening together, okay. Now I go back to Kendall. This year 2018, he did exactly, he now said protein evolution, in fact any evolution depends on its stability and abundance, and he talks of selection pressure, that is when at a given condition, at a given time, you have a certain distribution of, just like my distribution in amino acid, and you have a pressure, that means certain selection is taking place. Because of that selection, and you have a large, he did this calculation with 50. And of that he can be hydrophilic and hydrophobic, and I will come back to that. Look at what, just here by the selection pressure, which is same as my U, he comes and he has 50, so it is little less. If you 100, he would have gone to 10 to the power 20 billion years to less. So now he used our model to do evolution. So it really is funny to me, because we started with evolution, Darwin and Richard Dawkins, and went to protein folding. Now Kendall comes and does our theory to do evolution. It can be developed much faster, much greater. There is a beautiful book, beautiful Journal of Chemical Education, please read that, that came out 2014, where they did exactly our thing, correct, incorrect, by this person. Whole book was on our Leventhal paradox, our paper on Leventhal paradox, and he pointed on a very important thing, that the most stable state is entropically stable. This is the disordered state, and this is a funnel, because this is energy, this is entropy, and where entropy is minimum, energy is minimum, entropy is also minimum, and here entropy is maximum, energy also minimum. Remember, delta G is E minus T delta S, or delta H minus T delta S. So I can stabilize something by enthalpy, or I can stabilize something by entropy. we call enthalpic stabilization and entropic stabilization. Okay, I am still doing undergraduate thermodynamics. And he said that itself, this model itself has the folding funnel. So around the same time, a beautiful theory of protein folding was developed by very physics oriented ideas by Onuchik and Wallines, and that is this rugged. They said that this not just funnel, this is a rugged, and we will talk about funnel little bit more as we go on. And they also showed it is a funnel. These guys have a book on proteins, very famous book, came out 2-3 years ago, where the whole chapter of protein folding and everything was in terms of the monkey and the Levinthal paradox and our paper, the title of the, from title of the chapter or title of the section, it is about, they call it ZSB model, Biman Bagchi model. I didn't know of that, one of my students sent me that. Now, there are some very interesting things about this ruggedness that I'll spend a little time. Why these people said it is rugged? Rugged means the wrong contacts being formed. When protein trying to fold, it goes to a wrong contact, but stable, somewhat stable. They are very dangerous. These are the things like you are making a wrong match, but that match is quasi-stable. They really slow you down. So ruggedness can really slow down things, and evolution has smoothened them out. So the proteins that you are seeing now are less rugged. The protein that you are seeing now in this world, in your body, are mostly smooth. Okay, ruggedness has been moved out. Similar thing goes to DNA, single strand DNA folding. There, very easy to show these minima, because if you have a wrong base pair formation, then you will have these kind of minima. So there are certain, same analogy comes, Peter Wallines and Onuchik got it from spin glass. Their glass is this rugged landscape. Glass is you can have a stable glass. It's very popular these days, where you have a deep energy minimum. Otherwise it is rugged, and this is the artists, many thing of that is ruggedness. My boss long ago said that why ruggedness is important, that it has a square dependence on the energy of the ruggedness. Usually Arrhenius gives E by kBt, but this has a square, so it is, penalty is huge. For example, when epsilon is 2, you are compiled e to the power minus 2 to e to the power minus 4, 1 order of magnitude difference. Now I will tell you a little bit about the cooperative processes that Ken Dill talks about, that how does it form. Ken Dill in his paper, I cannot go back, it is too far, but he particularly talked of one important thing, which is hydrophobic and hydrophilic contact. So protein folding is coming from here to there, this process. This is a very nice thing. As I said, evolution of protein depends on stability. The proteins are selected by natural process, just like we are talking of Darwin to protein folding to again Darwin. What do I mean by that? This really, you guys will enjoy that. This is really very nice. This is done by Ken Dill and by one of our famous guy whom Rajosh is trying to get, Dev Thirumalai. These seemingly random, these are blues are hydrophilic. They like water. These should have been red, but these black ones are hydrophobic. They don't like this. But hydrophobic things like each other. That's called hydrophobic attraction. I'll talk a little bit of hydrophobic attraction a little later. Now, this now tries to fold. Does it go there? This is not stable. Does it go there where hydrophobic guys are exposed? No. Hydrophobic guys are exposed. No. It goes here. Look at the pairing. Hydrophobic, 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 hydrophobic. All hydrophilic are facing water. This is essentially protein architecture. Inside is the hydrophobic core. Outside is mostly hydrophilic. Outside are both hydrophobic and hydrophilic, but inside is all hydrophobic core, 90%. Okay, that gives its unique native state. So this is the unique native state. Now let me go back. Do I know from here that it will go there? After I tell you everything, yes, hydrophobicity, all these things, and there is a hydropathy scale. You can tell me yes. But you look at it first glance, you think it's a random, seemingly random sequence contains this step, and evolution picks up these things. That's what is important. When you say protein has been perfected by evolution, this is what we mean. These sequences survive, okay, and perform in your body. Okay. Now I give you another very tiny little nice thing. Simplest hydrophobic polymer. We consider, okay, let us see if hydrophobic at all can generate a structure. After all, protein is so much more complicated, so much more complex than by again theologists, Paley's things, such complex architecture. Hydrophobicity alone can go halfway. Okay. So we simulated, turned out we were the first one to simulate. That was really funny. Both went to one JPCL, I think another one JPCL without any referee reports. So we did that, this sequence, and we varied in. So they are nothing, they are just carbon. We call it a unified field model. Just this little thing, we simulated that in water. This again at the same time when I was doing protein folding, I was involved in a project in a single molecule spectroscopy and freight in this very different problem, conjugated polymer, MEHPPV. And there I realized that they don't form a Gaussian polymer. Instead, they kind of rods and toroids, but punctured by defects. So these kind of structures are the one they find out from single molecule spectroscopy. So that also gave me, so I was really very intrigued that here one case is completely material science, MEHPPV, holography and organic semiconductor, and then on the other cases protein folding. Hydrophobicity is key to all of them. So it was very, very interesting. So formation of order structures in hydrophobic polymer. So we simulated. C20 doesn't do anything, it fluctuates a lot. By C40 you start seeing some structures, and C100 beautiful coarse structure forms. This is the maximum we do to AMD. Then with the BD simulation also we find this kind of diagrams. It's very interesting. This goes like that, then these forms, then other one bends and goes exactly in between, just like we saw in my pictures. Beautiful structures form. This is the work of Suman Chakraborty and so these beautiful coarse helical structures form out of pure simple carbon chain. Some study of the free energy minima, how the minima comes, how the collapse state becomes more stable with long chains, and these are certain analogy to protein folding, because protein folded stable proteins are typically not lower than 30 amino acid chain long. I was talking of ruggedness, that ruggedness is very, very important. So, and it slows it down. He was always famous for these simple calculations. He did these calculations. He said, okay, let me take a harmonic potential like a protein folding funnel and I put ruggedness. He took this whimsical example and then he said, let me now see how long it takes to reach here. Say this is native state, how long it takes. He did that and found a very interesting thing. Forget about the equation. He found that if it diffusion here in this landscape, if these were not there, then if that is D naught, then ruggedness is by distribution, ruggedness flows down dramatically, square, okay. As I already told you, if it is 3, then 1 is 3 and there is 9, 2, 1 is 2 and there is 4, 2 and 4 here is factor of 10, okay. So then we did something. I was very intrigued by these things, and in doing the calculation, Zwanzig made an approximation which is called coarsening or coarse graining. He kind of took a little region and he smoothened it out. I was suspicious of that. So I said, let us do a simulation of that. Little did I know how difficult these things, and little did I know what I am getting into. It took us 4 years to get a result. What I constructed a random, it is very popular in solid state physics, is a random energy model. And now in that model I tried to, and we did not get convergence for 3-4 years. And by halfway we realized that because these beasts, if I randomly create maxima and minima, then I land up Once a while, these configurations where one minima is flanked by two maxima, one minima flanked by two maxima, they are the traps. I call it three-side traps. However rare they are, these traps control and slow down dramatically, and then my random walker, this is my random walker, it doesn't go anywhere. This is called breakdown of ergodicity, very common in the glass science. So we did a lot of work. Finally we got something. Then at that time there's a beautiful thing that came from two mathematicians, Newman and Stein. I don't have that one transparency I should have had. You know mathematicians, they are really amazing people. You know, there's a story in Feynman's book about mathematicians in Princeton. You know, they are very good people. Einstein have a lot of fun of, he himself was a great mathematician. He was, he got I think 5th or 6th in that famous Portland or Portman, that they're big mathematics things. Now, he said that he used to go at a coffee, there was a coffee with mathematicians and physicists all together, and these mathematicians are always discussing themselves, and they are saying, one guy is explaining, says, other guy said it is trivial, it is trivial. So whatever they understand something, they say it is trivial, not it is okay, it is trivial. So Einstein proposed a theorem, all that mathematicians can do is trivial. It is in the story is in his famous book, You Must Be Joking, Mr. Feynman. Yeah, some of you must have read it. Now, two mathematicians, Newman and Stein came to Bangalore to give a talk, and I have a good friend, Srikant Sastry, knew I am interested in this, and he told me, Biman, you must go and listen to this talk. Now, who goes to mathematics department? At least I don't. So, but anyway, because of him I went, and I kind of justified not going because this guy gave a talk with one slide, you know, one slide and board work. But then he was doing exactly the same problem. He was saying, he was giving these examples, beautiful figure, I don't have it, that if I have lakes, many lakes, they are connected, what it takes for the water of the lake to flow to the sea and from water coming from sea to the lakes. Then he said that if they are connected, I can arrange in 1D, then it is very easy for lake not to go to sea if one of these connector breaks down. That is the pathology of one dimension. So he said diffusion in 1D is pathological. So we were more interested then Zwanzig's, I'll show you, does not work. But then we worked with the Japanese, I think we have this equation, simple corrections of this three-site model. I could derive in board of this beautiful term, but I will not do it here, that it's how it comes from this error function, but no extra parameter. And this is Zwanzig. This is Zwanzig. Does not work too well, which I suspected, but took 5 years to show. And this is our equation. And sure enough, this is now beautiful. I think many other things we have done, dimensional dependent pathology and all these things, and so we will not go much into that. I will just take two little things, I will talk and stop. This is now, I have about, so I will take 10 more minutes. Okay. One is hydrophobicity. We talked a lot about hydrophobic, and this is a very big thing. So here they have taken a surfactant and put a gold tip and these things and a hydrophobic thing on top of that, and then they tried to find the force between them by atomic force microscopy, and they found there is an attractive force between them of the order of nanometer scale. Beautiful experiment, it came out in Science or Nature, whatever, beautiful, wrote Science, beautiful experiments, several things. So that got me really interested, that why is this, there is Nature and there are few PNAs, and these experimental results, this attractive force with distance, this was not correct fully, it was corrected later, it is not that big distance. So then I was interested, because there is a theory which talks of this in certain very complicated statistical mechanics way. I said, okay, and I can explain that I am not going to do that. I took a very simple thing, which is two-dimension sphere, each has 3 bonds. These are hydrogen, supposed to form hydrogen bonds, three directions. So It is minimum when one arrow points to the other arrow. That is supposed to be hydrogen bond. These are called Mercedes-Benz models because of this arrangement. And this whole model is called MB model. Beauty is that if you have, this is a very nice, it is so nice, let me write in board. So, this is a hydrophobic, it is a 2 dimension, though this is just a hydrophobic rod. This is a hydrophobic rod. Now, I have this my Mercedes-Benz model, Mercedes-Benz model. Now, if a Mercedes-Benz model comes here, it points in this direction because by sacrificing one bond, it can form the other 2 bonds. That is the minimum energy. Otherwise, 2 bonds will be compromised. Here, it forms these like that and these 2 this way. That means it creates a orientation which is orthogonal to each other. Now, the orientation that created by this guy propagates inside, and the opposite orientation created by this guy propagates this side, and they interfere destructively. As a result, hydrogen bond gets destroyed there, and that is the reason of the attraction. So, it is the in difference to the rest of the earlier work of the we proposed that, and there it is shown how the orientations are opposite, and then that is seen here, and some beautiful because of that they arrange and some ice-like structure forms, hexagonal rings. It was very nice thing, and then it's kind of experiment. We got the kind of pressure is the force kind of thing they did in experiment with several papers we wrote. Okay. So, the main message here, it is the orientational correlation of water and orientational heterogeneity that gives rise to, because these are real orientational complex orientation functions that give rise to the hydrophobic attraction, not the density which was some other people have done. Then we went ahead and something very nice that, okay, can I quantify, now go to protein, go back to protein, can I quantify the hydrophobic interaction between the proteins? We know alanine is hydrophobic, phenylalanine is hydrophobic, valine is hydrophobic, but we know there are other things like methionine, aspartate, they are hydrophilic. So, we got a very general model. That time it was one of the most general model, but it was also done by Sharega at the same time. It was Sharega visited Bangalore, I went and saw him and told him what I have done. He was really surprised because he was doing the same thing. Then we found out what we did. We took all the protein data bank, some 5,000 structures in protein data bank, and then he is now a professor in ISAR. All the names that you see are now professors in many different places. And we did something which was done in 1900, 1920, 1930, form your own potential. This is called knowledge based potential. So, protein data bank, we took the orientation, did a statistical analysis, and we found this beautiful result. Phenylalanine, they attract in protein data bank, the way they arrange, there is attraction, huge attraction between phenylalanine. Look at 2-hydrophilic lysine, there is a exact Coulomb's law come out. It was amazing a result of that. And then we look into, okay, let us simplest protein HP36, yes, there are 3 phenylalanine, 7, 11, 18 position, they are just packed just like that. Okay. So, this chemical unfolding we do it, it was published in a memorial issue of Paul Barbara, my very good friend. The energy landscape I was talking, all the same protein folding luggage landscape that comes out of this kind of potential and a theory. Okay, last part, 5 minutes on that. These are all in the result. That this is a very beautiful work. 2 papers. It was selected in Nature, but then we already published because we had some pressure for a special issue of Heinz. Me and Sunny published it already. So they called and told that we are not going to take it for Nature, but we will give it in Nature structural diffusion of protein along DNA. This was really beautiful work. So what happened that when you smoke, I hope not, I have given up smoking, so I am very much in the other camp now. But for long, I was told that, I was telling the joke today that one person tells you that if you do not smoke or drink, you live longer. The person who smokes and drinks told, yes, it must seem awfully long. So, but anyway, you shouldn't smoke. If you smoke, you generate oxyguanine. And oxoguanine is bad for you, it's cancerous, okay, because guanine gets oxidized because there are all these nasty radicals when you smoke. You know, it still pains me to talk of these things, but so this reactive oxygen species oxidize oxoguanine. But then see, people don't tell one thing, those who are against smoking. I am not really at all telling anything for smoking, don't get me wrong, but what they don't tell you, that there are these good guys in our body, these characters like HOG1, it goes and it reduces back this oxoguanine to guanine again. Nobody talks HOG1, nobody talks of lax pressure. Look at internet as if nothing is happening, you know. No, our body is playing a role. However, in order to be active, HOG1 has to find oxoguanine. How does it find oxoguanine? That's a huge problem. Highly efficient search of specific binding site. The search time is 100 times shorter than one would guess. It is Molokowski. WSK, I guess, is very old transparency, because I couldn't find my any new ones. Biomolecular reaction. This was first thing was done by Eigen, Manfred Eigen, you know, famous Eigen. There a model that was done by this. They assumes that the way a HOG1, the corrector protein finds the bad place by sliding along, but that did not was in bad. So one finds really how your protein moves. I don't have that slide, but they are beautiful. I've seen in your own eyes. You can see the protein moving because you can put a fluorophore on the protein and you can see them sliding along the DNA. DNA is stretched, elongated by a flow. These are called microfluidic experiments, and you can find out the pH dependence, you can find out the mean square displacement, you can find the diffusion. But their result did not explain because they had hydrodynamic model. When I saw the very first time when I heard the result from Sunny Z, I told him that it is not going to go linearly, it will go around like a helical fashion. Okay, I have a little movie of that. So it is not like sliding up and down. It is not like that, it is more like that, okay. It is more like a Mexican hat kind of a model. That's the way it is, barrierless reaction. So this is the way it is going in a along a helix. It is not this kind of a random thing, okay. What is the difference? The difference is huge. If it is going like that, it is rotating, and if it is rotating, then far from it is creating a flow which is called rotational flow. Rotational flow takes very lot of energy to create, okay. However, this is much easier, this is a linear flow. So I derived an equation which was the diffusion along a helix with slide. Before people had only this term, no, this term. So the other term, particularly comes in, and this is 1 over r. You can see data is everywhere, and with my equation, this suddenly collapses, really magical, and these are real, and these good guys are here. See HOG1, these are many good proteins who correct your body. But we found one thing, when it going along, it has certain randomness it faces, because see, they are all different. DNA here is there, base to base changing, and so their ruggedness. That ruggedness we found out by exact fitting to this, and this is a kind of ruggedness. This is the energy barrier. All energy barrier are very small. So it comes to the conclusion that these things are all over the evolution. These are the derivation. I don't need to go through all this. Pretty nice stuff though. All the diffusion, everything. So I want to end now. So this is Bob Zwanzig. I was looking for a picture of my own father to put in because he started many of these things very young age without knowing, and my good friend Paul Barbara. And I have written 2 blogs on him. I have written, I think, 1 blog on him. Please read those blogs on Paul and Bob. And this is the one, Seki, who did the random network, Ornov, many things for initial study of protein folding, and the phenylalanine, the hugely attractive potential, all these things of him. And Sumon did the polymer work, and he did the hydrophobic force law. Tuhin and also Tuhin did that. Rikia and Shushmita, I did not talk of their work. They are all, these three all are faculty. They are enjoying life in Germany, they are husband and wife, and they are not, I think, any intention of coming back. He will defend his thesis soon. Shushmita is looking for job. He was in a Rice University with Anuchik and Walines group. And this is the present group. And it's very interesting. We took the picture recently. There is some really good guys are here. Pooja, Shomok, Sayantan. He submitted, looked a little scared because that was just before their submission. Thank you for your attention.
All the structures in the protein data bank.
Right.
You look at the distance and
Exactly, orientation and distance, and this is called formation of knowledge by potential. There are some work done by, I can give you by Melo and some people whose formulation we use. So the person whom we talk it are no, but you find there are two papers, and our paper will have the references to a guy called Melo. So we will use that, and they formulated essentially you do Boltzmann weighting and then do a statistical analysis and you get it out, which was amazing. That this is okay. I liked it, but I really liked the A part, negatively charged Coulomb part. 1 over R comes out. That was just, and that's amazing. And in orientation depend when they are close to each other, but far from them, they all converge. Sure.
So when you had this typing example, like, and then you said this penalty for wrong, right? So at that time, what did you think of this penalty as like a
Yeah, in most of the cases, it is is a little complex. But let me tell you, when I told you, when we tried to do protein folding, we had our own potential, and many people told us to make them something out of this, but we just playing games. Then we took the hydropathy scale of Key Doolittle and then the helicity propensity, and we formed our own force field. And we did HP 36. As I told you, we did 1000 and we could not get any RMS, the deviation more than something like 2.4 angstrom. And we found the following reason is the main thing. In a 36, in a 35 position in one end is there is a isoleucine. What happened when they form, this isoleucine has to go inside the hydrophobic pocket. Most of the time during the collapse, it just stays outside. Only 3 or 4 we found, if you simulate long enough, they ultimately use a rare fluctuation to put their head in. So what finally, so mistake is either wrong hydrophobic contact, and they form very near the native state, these mistakes are forming. There you already have lost much of your entropy and you have gained lot of enthalpy. But it is this matching between the two very delicately that is to be done. So yes, hydrophobicity, relative difference in hydrophobicity, and that was the point of Candide also, that over the years selection pressure, which is same as our U, picks up these kind of things. So some see, we always talk, these sequence is conserved over evolution. What does it mean? That this is selected by evolution. So these are the little molecular level interactions, like HP 36 I give you phenylalanine 7, 11, 18 just forming a hydrophobic core, beautifully oriented. This is the basic molecular basis of the architecture that nature uses. And go back to Dawkins, really, that is these laws of nature. That's the blind watchmaker. Yes.
What happens to this Wong-Fritz relation in 3D?
Nobody can do it now.
Numerically.
Numerically 2D we did little bit. You can easily say that they become better, because higher dimension means mean field approximation works, and what Zwanzig this is mean fieldish because the coarse grained, it becomes better. But there is, of course, Zwanzig did not do it. Zwanzig approximation will come with a degeneracy factor in higher D, which we have not done, but when you go to higher dimension, I can show you 2D, 3D, then Zwanzig 1D becomes worse and worse, but so Zwanzig remains in higher dimension, Zwanzig remains here. See 1D, these are exact results, simulation and our more complicated theory. So 1D, 2D, 3D, infinite D. So the one dimension is pathological, and Newman-Stein, you can see it is really pathological, but 2, 3D they group together. Zwanzig would be here, so he would not work. So this is Zwanzig, so he would not work. But then it's very unfair, because to use just Zwanzig things which was done for 1D, one has to do it for 2D, and there is a degeneration factor that will come. I think that will make it look better. Yes. Right.
So when you're approximating that some of these will not exist because the stereotypes are there and the electric it's a gradient kind of your hair. So it's not like completely random because of the way they are arranged, where the sequence is arranged.
See, no, not quite. See what you are seeing today. What you are seeing today in 2018, all the proteins, they have already passed through huge amount of evolution test. So what you are seeing, they are already optimized and selected. Now if I randomly generate, they do this, if I randomly place amino acids and 100, and people have done this, they will never find a native state.
Yeah, because it is also in the stereotypes of the native state.
Of course, those things, exactly, that's why, yeah. See what I said, each amino acid has randomly 3 states. In real world, those 3 states will be weighted by electrostatic interactions and a periphery of it. So then my simple equation will become little bit more complex. There are many ways it has to be improved, but then as soon as I do those improvement, I won't get a closed form analytical solution. The story will become more complicated. Sure.
Many proteins require chaperones.
Yes, absolutely.
Now, if you want to include a chaperone contribution, that means they're not naturally, if you leave them by themselves, they're not naturally folding.
Of course.
Either adding interactions or potential or something like that to make them.
Sure. That is what. Sure. That's what actually Rajoshi, who suddenly left. See when protein goes to an extent like this, larger proteins, then they get stuck in a minima. You need the chaperones to get it out of the minima.
Or you can grab some portion which never falls first.
That also it can do. So you can, so it would be in our model, it would be, multidimensional consideration, higher dimension consideration, and then you need the similar ruggedness, and it would be this kind of simple mathematical models, or you can call it toy model. It just gets very, very complicated. But people have done these things now, the role of chaperone in protein folding, and then Peter Wallines has done the random barrier model of these kind of things. And what I am saying, once you know the end story, the role of chaperone, it's not that difficult to build a mathematical model, but it loses its charm.
Has somebody shown that protein which requires chaperone has a rugged landscape as compared to one which does not, because it has more traps?
See, I told you that just right now people are beginning to fold a protein which may be maximum 50 or 60 amino acid long in computer simulation, like there is called David Baker and David Shaw. They are doing that game, and there was a Few years ago there is a science paper where they showed they can fold 12 proteins, but they are all up to 50 or 60 amino acid long. I do not think anybody has done it from any kind of first principle or understanding of showing the role of chaperone. I can imagine that there is a two part of the protein which folds or goes to near native state and gets stuck there. Then I can imagine a chaperone comes and allows, for example, one particular isomerization reaction which allows it to fold. So usually gets stuck in a minima, same like I told you HP36, it gets stuck in a configuration, then it needs help. Help means, that means it requires a very large barrier which it cannot take care itself. So if you look into molecular level thing, then again you will find the same kind of hydrophobic or hydrophilic things. You might find a hydrophobic coverage where it can take place. The basic, what I am trying to say, that the old Richard Dawkins, that he said the blind force of nature. What I am telling, all these hydrophobic interaction, which Kendall also said, hydrophilic interactions, your electrostatics or static things are all just examples of that. These are the forces of nature that Richard Dawkins talked about. So in that spirit, you should take it. Yes, details we can work on, and details will be worked out. Yes. Yeah, but of late, in protein folding, people do not think it is the uniquely stable structure. That's one thing I said that I'll come back, but I am very happy that you asked that question. This is a very deep water, so and my very favorite thing. So this is one. You know, in physical chemistry, in my book, very first chapter, we have something called response function. Response function is determined by fluctuations, and like water has large specific heat. Why? It has very large scale energy fluctuations. In the protein sample also, the Kendall argues that the protein that are essentially adapt and survive the sequence are the ones which are not the most stable, so that it can fluctuate around. Right now in enzyme kinetics, people believe that the proteins are near the native state, but it is really fluctuating around. So there is a lot of mobility that is required. So in the selection, that basis will be survive the, you know, in the fitness parameter, those which have certain flexibility. So a population, for example, the logic the people say that if a foreign alien comes with a bacteria, Indian population will get wiped out because our caste system has not prepared us with the diversity. But in Americans they will survive because they have the diversity. So diversity of the population also important. Yes, a particular subset is selected, but they need to adapt. I think selection pressure at the molecular level, that I don't think. Okay, one, I would say that it is all undergoing mutation. I am working at the level of protein, though ultimately you have to go back to DNA. So at the level of protein, what Kendall argued, the hydrophobic hydropathy scale, that mutation which gets the pairing of hydrophobic groups, but at the same time it is possible to improve by opening up. That means if it is too stable, then it is not good for you. So the ensemble which has near the bottom, but which can at the same time get mutation to survive, that is the one which are getting selected. So he said the most stable protein sequences are not going to be selected. So I recommend you read the Dill paper. It is very new paper. It just came out few months ago. I myself still reading it because they use my theory. Hydrated gas phase or just gas phase?
They need basically this diesel assisted
Evaporation.
proteins, now the
Mm.
starch proteins, the charge,
Yeah.
charge, and those charge proteins what they give you the kind of line, and they look at the
Yeah,
time,
yeah, yeah.
and then they incorporate simulations and form. So under that situation, can you comment on?
Yeah, in the absence of water, I don't know. I know Toronto school they did the polymer. Yeah. They did because that Michael Klein pointed out after our paper was published. Yeah. You know, I can understand weak hydrophobic attraction. In the gas phase, the molecules will be like to close to each other because of Lennard-Jones interaction, irrespective of water. In water, that effect becomes much larger. So, gas phase, I also expect certain reorganization. So, it is something like my Brownian dynamic simulation where I don't have water. Okay, like structures are different, but I do get reorganization. If I can get there, yeah, not bad. So, in this structure, this has no water, but they have Lennard-Jones interaction. Only this one. They are all with water. They are fully atomistic simulation. But this is the Brownian dynamic simulation, BD. This one. And BD we get up to 200, 300 we could do, but not more. But what happens when you become bigger, then they get trapped in certain minima, but that means it's not ergodic. We don't get the most minimum structure unless you do Monte Carlo simulations, which you didn't do. What Ken Deal said that if the most stable structures do not adapt and they are not at the height of the fitness landscape. So, he is now explaining, he is giving a molecular version of the fitness landscape. Now, why is that? I would imagine the idea is that if I am more stable, that if my surroundings changes and the selection pressure is brought in, I won't be able to adapt.
The selection pressure at this level is the same as the selection pressure for the inhibition, right?
At this level, in the model level, yes, each guy gets a like you, we have, each guy faces a uniform potential which can be random, but that is at the simplest level. So, now all of them have that, but now say I can make it random. Okay. Now, there are some mutation. If the mutation is made, then its fitness increases under that particular pressure. To what extent the randomness or specific, what you are asking, along the sequence, each amino acid is getting individual different pressure. A mean field calculation like that can be done, but I doubt Ken Deal did it. What I could see from Ken Deal that it translated our work by equating our U to their selection pressure. And they said, like, you can consider it a Ising-Spring model, and you are saying whether I have to, when I have to put a magnetic field, then whether my spin can flip. If it can flip, otherwise stable network, then you are more, you can adapt. But if you cannot flip, you cannot adapt. Yeah, that's the way Ken Deal didn't say that. That's the way I am interpreting right now. My understanding of it Kendall's work to my work, I was fascinated by the fact that he uses our theory to do his calculation. I am not supporting his work, I am just drawing analogy what I understand, and the tremendous same graph that he produces, which I produced in Leventhal paradox many years ago.